Morning, everyone, and welcome to this session on in Physics 101. Today is Monday, November 14th. We are a week before Thanksgiving. We still have some materials to cover. This week, we're going to focus basically on the atomic model, the early history of the atom. Today in the lab session, we have an important session. It's a discussion session. We're going to cover basically 4 chapters in terms of the materials, in terms of math, in terms of problem sessions. So yes, there will be some calculations in it. So please be ready to do that. It's going to be very helpful for exam 3. So attendance is required because lab sessions are not recorded. So if you miss the lab, you basically you're going to have issues because you're not going to have them recorded or anything like that. So again, it's all a discussion session. It's on the 4 chapters, basically dealing with electricity, dealing with currents. I mean, the first part is electrostatics, really, that's what it's called. It's the interaction of different charges. The second part is electric currents, basically when you have arrangements of different resistors and so on and so forth. And I know we did a whole lab on that. And also the third topic is electromagnetism, especially magnetism. So you will have also assignments in there. And finally, the last topic that will be discussed today also in the problem session is today's lecture, namely the early atom and the atomic model. So this is basically what the whole session is about. And as I was saying, this is very helpful for exam 3, which is going to happen, of course, after Thanksgiving. So this is in terms of the assignments, in terms of the stuff that we have. We normally have the stuff that, and the discussion session, of course, it's still required that you guys have to do it. The only thing is some of these assignments are due after Thanksgiving. So the Thanksgiving week break is next week. So hopefully you guys will continue basically completing your assignments in time and so on and so forth. So let me prepare the material for today, namely the let me share screen. Share. So again, today's topic deals with the early model of the or the early history of the atoms and how the atom came out to be. Because one of the things that you guys know, at least the current model that we have for the atom, is you have somehow a nucleus in the center. It's my pen, I'm losing there. Anyway, so you have a nucleus somehow, okay, and you have a cloud of electrons that swirl around the atom. Now, note the following, that this is not, I mean, on the plane, probably it's better to be drawn as a circular path or a circular cloud, as you should say, but this is actually a spherical distribution of some sort. Now, there is some distribution. There is some symmetry in it, so it may not be completely a sphere, so it may it will retain that distribution of charges somehow. Anyway, I'm not going to try to get into the idea of the orbitals, but the point in here is there is a cloud of electrons around a nucleus. Okay, this is the current view of the picture of the atom, and they are too small. So that's what we know about them. We know the size of the atom is of the order of 10 to the negative 10 meters. I'm not saying it's exactly equal, it's of the order of 10 to the negative 10 meters. This has a name. This, they call it angstrom. Angstrom. Okay, so this is the size of 10 to the negative 10, or it's just 10 to the negative 1 nanometer, basically, because a nano is 10 to the negative 9, so you have to add another one. So that's the size roughly of the atom. Okay, so this is the size of the atom. okay, meaning the entire atom from end to end. The nucleus is positively charged, the electrons are negatively charged. So that's what we know today. So the electrons have a charge of 1.602 times 10 to the negative 19 coulombs. And it's a negative number. So this is the electrons. Inside the nucleus, there are two particles. One of them is a proton. And the proton has a charge that is equal to, so if this is the Q for the electron, namely the charge of the electron, the charge of the proton, it's the opposite, that's all. It's a positive 1.602 times 10 to the negative 19 coulomb. Whereas the other particle inside the nucleus, so those are inside the nucleus, is the neutron. The neutron has a charge that is 0. So this is inside the nucleus. And this is the electronic cloud. So how many exactly electrons you have? That depends on the material. If you're looking at a neutral atom, for example, from the hydrogen, you have exactly 1 electron. If you look at the other side of the, yeah, if you look at the other side of the spectrum, namely the helium has exactly 2 electrons. If you move on to the next element in the periodic table, namely lithium, has 3 electrons. The one beryllium next to it is 4 electrons. And there is a big jump. You go to the boron, okay, that has 5, carbon 6, nitrogen 7, oxygen 8, fluorine you have 9, and then finally at the end, immediately below the helium, you have neon. Neon has 10 electrons. So it depends on the element. Each element has Z electrons. Where Z is equal to 1 for hydrogen, Z equal to 2 for helium, Z equal to 3 for lithium, and so on and so forth. Okay, I'm not going to list all of the entire periodic table. Okay, how many protons each atom has? Well, it has exactly Z number of protons. This is for a neutral atom. For a neutral atom, the number of protons equals to the number of electrons, and both of them, they're labeled by the letter Z, okay? How many neutrons are there in the atom? That depends also on the atom, okay? The number of the neutrons varies from 0 it's not Z, it's N. What happened here to my pen? N can be 0, and it can be as large as, basically depending on the elements. Okay, it can be very large. Note that because it has no charge, this does not impact the chemistry of the elements. Neutrons do not impact the chemical properties of elements. As a matter of fact, the entire nucleus does not even contribute to the chemistry at all, or the nucleus is too dense inside, and it does not participate in any chemical reaction. I mean, it's involved in nuclear reactions, that's true, but not in chemistry. So this is basically what we know today of the atom. But how did we get in here? That's the big question. Okay. How did we get to this model? I mean, right now I have a nice periodic table with all kinds of the elements arranged in here for the entire column in here. Okay. And then this is column, which is the its group has its own label in here, and then you have each or they are aligned also on a rows that determine also their chemical properties. How did we get all of these things? How do we know all of this for sure? This is correct. Okay. Well, it really evolved. So the whole process evolved over time. Okay. So the knowledge that we arrived to at this point came after a long time, basically experimenting with different substances. I mean, the idea is very old. It's actually from the time of the Greeks, if you really want to. So when you think about it, at least in the time of the Greek philosophers, so what they said is the following: if you take a substance, it doesn't matter which, okay, and you cut it in half, at that point you end up, of course, with half the substance. Then you cut this one in half, and at the end, you're going to end up with only half of it. Okay. So ultimately, you're going to reach a point where the smallest portion of that substance that cannot be devised, this is what atom means. Okay. It's coming from, I think, the atomus, which means that non-divisible. You cannot devise it any further. That's it. It's as small as it can get. And this was true for all materials, okay? Whether you're looking, for example, for iron or for wood. So you're going to take a piece of wood and you start chopping it until you get to a point where that piece of wood is as small as possible and cannot be chopped any further. Meaning if you break it any further, it's going to basically lose. It's not going to be wood, so you cannot actually break it any further. So that's the difference actually between modern view of what the atoms are and what the old basically picture was. Obviously, that was based on philosophy, not on experimentation. So it was until like the 17th century, 18th century, when the idea of gases people started working with, and Mr. Lavoisier basically came up with his law of how basically materials, they stay in proportions when they interact with one another, and also Dalton. So all of these ideas came with the, it looks like the atom, the model of the atom is really based on some sound, basically observations. So now you have a picture that's starting to emerge, okay, with that. Further combined with the other experimentation, other techniques also involving vacuum chambers, okay. So if you place a cathode on one side and an anode on the other side, this is positively charged, this is negatively charged, this is what we know today, and place a high voltage in here, a small battery will not do. So you really have to have a big power source in this case, okay? And if you produce high enough voltage, sparks will fly. In a medium that is not completely in vacuum, but rather with unpressurized, if you wish, or pressure, basically you remove most of the gas, not all of it. Okay, so now sparks will go between the two ends, between the two nodes, if you wish, inside in here, and those charges basically they produce light, just like lightning. Okay. Depending on the density of the gas, of course, that's how light is going to be produced in this case. Even for an inert gas, even a gas that does not conduct, okay, that's actually the whole idea for it, for an inert gas. Inert gas, for example, of those elements in the last end of the periodic table, like neon. Actually, this is how neon light works, okay? That's how neon lights basically work, okay? They use this technique. Obviously, helium at that time was not known material. It was discovered later on, so that you have an idea of how these things were. Anyway, the point being in here is that if you reduce if you reduce basically the gas inside the chamber in here, which is usually made out of glass in this case. If you reduce the density, namely remove more and more air in this case, so what happened in this case? Well, there is a glow that starts to appear on this end, on the cathode. This is the anode, by the way. So that glow was later on named cathodic rays. So what happened? If you switch the polarity, if you change the polarity, it seems always it's following the cathode. That's why it doesn't show in here, but it shows on this side. So that remnant glow that starts to appear as if the onset of basically the spark, that is what is known as a cathodic ray. So Mr. Thomson, actually what he did was he experiments further with this cathodic rays, and he actually came up with a device that involves so here you have a screen. And on the screen, he has a fluorescent material. So basically what that means is if you hit it with fast enough particles, electrons, charged particles that we know today, that's what the cathodic rays turn out to be, actually, electrons. That's the bottom line of this whole thing. It's going to glow. Just like the old screens, basically. I don't know if you guys have seen that. I know that you're too young to have probably, to have seen that in real life, but we used to have them in the 80s, probably even in the 90s at some point, where the monochromatic screens for either TV or even computer monitors and things like that, they used to use this technique. So basically you hit it with a fast enough, and the TV in those days and the computer screen at those days were very, very bulky, very basically not as thin as we have them today, which use completely different technology. So what happened in this case, you get, you have a cathode at this end in here that produces those same rays, okay? So you have those cathodes, but you get them accelerated to a point in here where they're going to emerge at this end. So you have now a cathodic ray that is going to emerge, a beam basically that is going to form. And this beam is going to come, of course, and hit the screen if nothing else happens to it in here, and to produce a dot in the middle. Well, what happened if you have another two plates in here? So you have two plates. One of them is negatively charged and one of them is positively charged, similar to a condenser capacitor, but two plates basically. So you have like another battery if you want to. So you have a battery in here that produces a voltage difference between two plates, metallic plates. So if this were positively charged, obviously they would be repelled by the positive plate and attracted by the negative plate. So they will bend this way, and they will fall on the fluorescent screen in the bottom of the screen. Now, this is not what happened when Mr. Thomson did this experiment. So we're describing Thomson's experiment with this cathodic rays that were basically discovered. So what happened in this case, actually, it's the opposite. This rays bent in the opposite direction. Obviously, if he yanked I'm sorry, I think he doesn't matter. You can use a magnetic field or an electric field. It's going to bend in a different in a given fashion. So this is positively. This is the plate. This is where the anode is. This is where the electrons are going to leave the cathode, and they're accelerated by this electric field to come to this point. Of course, you have to have an opening in here for them to continue. Here, you could have a magnetic field, and that's exactly what he did. Actually, he had a magnetic field. And the magnetic field, of course, if you guys remember from the previous chapter, according to the right-hand rule, the charged particles moving on it will follow the right-hand rule. Okay, I'm just roughly trying to draw a hand in here. So this is the velocity of the particles as they come in here. So imagine you have an electrons that are moving super fast in here. So this is their velocity. And if you have a magnetic field pointing upward, in this case, they should bend this way. So you should see them impact the screen on this side. Okay. So think of it that this is actually a North Pole instead of this configuration. You could have a magnet in here. And I think that's how we did it, actually, with the magnetism and combination of magnetic field and the, but you could also use the electric field too. So the original configuration is possible too. But then I think his experiments uses magnetic field, and that's exactly how the old actually tubes are. The ones for the old TVs, the bulky TVs and the bulky monitor screens. They use actually a combination of an electric field to accelerate the electrons, and also a combination of a magnetic field that bend them. And how much they bend and what they describe on the screen in here depends on the intensity of the magnetic field. Obviously, they could go and hit the screen in the middle, but they bend left and right depending on the direction of the magnetic field and the intensity of the magnetic field. Okay, so if you have north-south or south-north, if the magnetic field is pointing downward, then the electrons will hit on the opposite direction and so on and so forth. It's a combination of electric field and magnetic field. Here is the deal, though. What Mr. Thomson did, actually, J.J. Thomson, because there is his son also worked on this field. So usually they refer to them, at least for Thomson. The original one is J.J. Thomson. If you have the electric field is fixed and known, if the magnetic field also is fixed and known, what he ended up doing in here, he found the ratio of the charge of these particles over their mass. Okay, so that's what Mr. Thomson did. He didn't find the charge of this particle, he didn't find the mass of this particle, but he found the charge to mass ratio. And this is interesting, because when he compared this one to another known material, namely the ions of hydrogen. So if you take hydrogen and you ionize it, you're going to get basically what we know today, again, from the original picture in here I was describing earlier. For the case of hydrogen, you have the number of protons is 1 and the number of electrons is 1. And for regular hydrogen, actually, the number of neutrons is 0. So for the hydrogen atom, it looks like basically you have for the neutral hydrogen atom, you have, of course, a proton inside by itself, and the cloud is formed by only 1 electron. I know it may sound counterintuitive to understand that, hey, how can you make a cloud with a single particle? But that's actually the modern picture that we have. But if you ionize it, so there is no neutrons for the case of the hydrogen, normal hydrogen. This is the regular hydrogen, because there are other kinds of hydrogen. There is the heavy hydrogen that has a proton and neutron inside. And there is actually another version of hydrogen that has 2 neutrons and a proton, okay? So we're talking about the normal hydrogen that is the main isotope of hydrogen. That's what they're called, isotopes. So if you ionize it, you get rid of this electron. So at the end, you end up with only a single proton by itself. So this is what's known. So this is what I mean by an ion of hydrogen. Obviously, it's positively charged, okay? That's what we know today, actually. So it's positively charged versus, so if you do the same experiment, but instead of putting in here a beam that is made up of these cathodic rays that were formed in these chambers that I was describing earlier, vacuum generated. It's going to bend in the opposite direction. So wherever the electrons bend in, it's going to bend in the opposite direction, and it's going to bend because they have far more mass. That's what we know today. They will bend less than what the electrons do. So the electrons have less inertia, so they will respond much easier to the electric field. So in this case, depending on the bending, the angle with which they're bending, he was able to compare the two. He was able to compare Q over M for the so-called cathodic rays versus the Q over M for the hydrogen ions. And this ratio, of course, he found this number, and he found this number, and he can find the ratio, and it's 1800. That's what Mr. Thompson had found. So either if I maintain the masses are the same, let's say, for example, I know the mass of this cathodic rays. Why do I have an H in here? Cathodic rays. If the mass of the cathodic rays and the mass of the hydrogen ions are the same, this is a big if, of course, the same, then the charge of the cathodic rays is 1800 times bigger than the charge of the hydrogen ions. However, this F is not what he thought it's true. That's not what he believed. His counterstruck this argument. He was thinking that the charge of the cathodic rays is the same as that of the ions. Therefore, the mass of the hydrogen ions is about 1800 times that of the cathodic ions. So two things emerge, several things actually emerge from this experiment. First of all, the cathodic rays are not rays at all. They are not waves at all. They are particles because they must have a mass in here and they have a charge. So these are particles now from this point on. And these particles, they have negative charge because they bend in this direction, not in the opposite direction. Furthermore, their mass, at least that's what he believed, is a lot less than that of the ions of the hydrogen. I mean, as that of the hydrogen ions masses. So that's basically the conclusion that he emerged with. I mean, there is another indication that maybe that the charges are not the same, but that he was inclined to dismiss, and he was rightfully so, because there were some other experiments, actually evidence for this, that the charges are the same. It's the masses that must be different. So that's really what the whole conclusion of all of his experiments. So now his experiments is coming together beautifully and everything looks good, except he doesn't know what the mass of these charges are, and he doesn't know what these charges are. So he knows that they are particles, later on called electrons, the units of electricity, basically, that's how they were called. So this cathodic rays now, cathodic rays, are what electrons are. So that's the name that started to stick to them. Okay, so the particles of electricity, that's what an electron is, what the word electron means, because they carry charge with them and they're tiny. And that's the belief now, they're extremely small. Now, He doesn't have any idea how big the mass is or how big the charge is, but he knows what the rate of the charge over mass is. Now, Mr. Millikan did another experiment, actually trying to come up to an understanding and help out with this point, with this process. So he came up in 1910 and suggested an experiment, basically, where he had a liquid, in this case, an oil, in a chamber, and that oil, basically, he created in it charges that he sprinkled inside, charges, and they're suspended in the oil, okay? Not really, I mean, they should fall. So he has an opening in here to read through these particles in here to look at them. And he applies, of course, an electric field in this case. And if he applies an electric field, then let's say, for example, they're all negatively charged. So in this case, they start to fall upward. If the electric field is strong enough. If the electric field is not strong enough, what happened in this case is they actually fall due to gravity. If you cancel the electric field, let's say, for example, there is no electric field at all, so gravity will make them fall to the ground. All of these particles, suspended particles, okay? And you need the liquid in here to have a little bit of viscosity to control their flow. And actually they have the particles, they have a shape that actually helps with their floating. Anyway, if he knows the viscosity of the fluid, if he can determine the force of gravity, he can actually tune the electric field so that they remain suspended. They don't fall, they don't rise, they remain suspended. So this is Millikan's experiment. Millikan, I think it's an E in here. Experiment. I don't remember the year. It's been a long time since I looked at this thing. Anyway, this experiment, basically, he monitors the particles that they're going up and down. And if he notices that they are mainly falling, he increases the electric field so that they start to probably rise. As they start rising, he cancels a little bit of the electric field until he sees that they are suspended in the fluid. That is when the force of electrostatic force in here that is trying to pull them up is canceled by the force of gravity that is trying to pull them down. So based on that, those calculations, basically, he was able to find the necessary mass for this, the charge necessary on these particles in here. And he found that the charges, when he plotted the data, it took him a long time to plot the data. And he found that all the charges are common multiples of a unit charge. And that unit charge turned out to be the number I put before, which is 1.602 times 10 to the negative 19 coulomb. So if you find all of the charges needed to suspend all of these materials in here, and you plot the numbers versus the mass and all of these things and those particles, you will find that this number, that all of these charges are common multiples of this number, 1.60 times 10 to the negative 19. So now you know what the ratio is, and you know what the charge is for the electrons. So all you have to do is determine the mass of the electrons. So this is what the charge of the electrons was. And of course, it's a negative number. The negative because of the deflections in Millikan experiment. They deflect toward the positive plates. And now we know the mass also after Millikan's experiment, and the mass turned out to be 9.11 times 10 to the negative 31 kilogram. So this is the mass of the electron. By the way, from here also you can find the mass of the hydrogen ions, because it must be about 1800 times bigger than that of the electron. So all you have to do is multiply this number roughly by 1800, and you're going to find the number for the mass of the proton also. So this is the electron. The mass of the proton turned out to be 1.67 times 10 to the negative 27 kilograms. So a bunch of things came up. So we know a lot at this point, okay? Obviously, Mr. Thompson came up with a picture that seems to work, and the picture is the following. Atoms are neutral. And since I have a bunch of these charges in here that are negative, I must have the same amount of charge that is positive. But the charge he believed is smeared in the atom. So the positive charge is smeared inside the atom, whereas the negative charge is localized in electrons. So that's the picture he imagined for so there is like a dough, for example, that is completely positive. So the dough is positive, whereas in this case I drew 3 electrons. The electrons represent the electrons. In this case, 3 dots in here represent the electrons. So this was later on named as the plum pudding model. And the reason why you need it this way is because we know atoms are neutral. Okay. So this is, in a sense, the picture that Mr. Thompson has off of it. So if in case, for example, you remove a charge in here, you're going to have a positively charged ion in this case, for example, for the case of hydrogen. And you only have, of course, 1 electron. But if you add up another electron in here, you're going to have a negatively charged atom and so on and so forth. That's the picture he had. But he had a problem trying to understand, for example, another phenomenon that was known at that time, based on these experiments in here, the ones that I described in the beginning. Unique gases have unique spectra, because if this light is emitted by the gas inside, you can run it through a prism, for example, and the prism can break down the light. So the light in this case that is produced will have unique spectrum, meaning unique lines in the spectrum in here, depending on the gas. So each gas produced unique spectral lines. Okay, so that's basically the idea also that emerged. So in this case, what he wanted to do is actually compare that to the spectral line. So his thinking is the following. He said that, okay, depending on the number of electrons, different gases from the periodic table that I was talking about in here, they have different number of these charges. So the arrangement of these charges, he's thinking, is the one that could lead to those different spectral lines. So if I have, for example, 2 charges, they could be like this. 2 electrons, they would be like this. 3, they form probably a right angle. I mean, they will form in all the sides will be equal, and depending on their motion and how they move, that is going to produce the light. So that's basically the picture that he wanted to convey, that 4 charges, for example, if I look at beryllium, 4 charges in the case of beryllium, they will form a square, and the way that these charges will move will produce the light. So that's a picture that Mr. Thompson came up with, and that is the model that he had. He had a student, Mr. Thompson, and that student's name was Rutherford, who came from what is that island next to Australia? Sorry. Anyway, that's his student. He wanted to confirm his model. So what he did was he came with a gold foil. Why gold, you're asking? Because it's very easy to make basically thin film out of it. And at that time, radioactivity was just discovered. And one of the radioactivity is polonium. Polonium produces charged particles at that time that are known to be exactly, their charge is equal to twice that of the electron. Okay. So they come in fast and they go through. So they're positively charged and they go through the material. This is what he was thinking. He was thinking because this positively charged inside the gold atom in this case, they have positive charges and they have the electrons are localized in very specific places in the case of the gold. So in this case, because the positive charge is distributed through, it's smeared throughout the entire atom, it's not going to impact this centralized atom in here that has a lot of charges. So it's going to hardly impact it. So what he expected, according to his model, is that all of these alpha particles will be basically collected in here on the film in here. So that's basically what in here. So this is actually a screen. Again, fluorescent screen, okay? So he wants to see, and this is the gold in this case. Gold has a symbol AU, by the way, okay? So he expected all the rays to go straight through with the completely unimpeded, okay? So that's the idea. And when he did that experiment, that's exactly what he immediately noted, that most, I mean, not in his thinking initially, that all of the alpha particles, these are called alpha particles, by the way, they are produced by radioactivity. Later on, it turns out to be just the ions of helium, helium, when you strip it of its electrons, it becomes basically alpha particles. So those are what these particles are. So he expected the alpha particles to go straight through, unimpeded. And initially, that's what he thought he has found. He has found that basically for all of the alpha particles went through. But he asked one of his students, actually, that's Rutherford's students, to check this region to see if we get any rays back, to see if we collected any of the alpha particles back. And to his surprise, and that of his student, and to everybody else, is that actually alpha particles bounced back. Some of the alpha particles came back. Some of them came back straight through from where they came, bounced immediately back. And that was that was a big problem. Because the vast majority now, according to the final conclusions, went through and impeded. But fraction of them, they get bent backward. Actually, some of them actually bent on this direction, and this direction too. And for the vast majority, as I was saying, they went through. Now, this suggested immediately something else, that this picture is wrong of how the atom looked like. Okay? That the atom is not how it's depicted in that picture, but rather it's slightly different. So you have, in this case, a nucleus. This is where the positive charge is. And the electrons must be going around, not inside like a dose structure, and there is an empty space in here. So what happened in this case, the alpha particles, for the most part, they go unimpeded, as we talked about in the previous ones. But some of them, they went too close to the nucleus and they get bent. Some of them, they actually bounce back. They go straight in and they came back. And some of them, they come at the right angle and they bounce on the opposite direction. So this is basically what happened in here. Based on the size of the alpha particles and their charges, all he did was use a little bit of collision theory in this case to find the cross-section, to find the size of this nucleus, how big it is. And to his surprise, the size of the nucleus is about 100,000 times smaller than the atom. So if you take this size of the atom, which I said earlier in the beginning that it's about 10 to the negative 10 meters, the size of the nucleus is 10 to the negative 15 meters. So the nucleus is 100,000 times smaller. So that's where the positive charge is concentrated. So this is the Rutherford picture now. The model that we have in this case is completely different. That we have a nucleus which is 10 to the negative 15 meters in size. This size, by the way, has a name. This is what is known as a Fermi. So when Fermi is equal to 10 to the negative 15 meters, remember I said when angstrom is equal to 10 to the negative 10 meters. Those are not common units. Of course, the common unit is the 10 to the negative 9 is a nanometer. 10 to the negative 12 is a picometer, but 10 to the negative 15 now has a name. It's called a Fermi, in honor of Mr. Fermi, who did a lot of work in nuclear physics. So again, so that 10 to the negative 6, of course, is a micro. Use the symbol mu. And then 10 to the negative 3, of course, is a milli. So that the some of these small sizes are. So 10 to the negative 10, that sits actually between in here. It's smaller than 10 to the negative 9, but bigger than the picometer. So this is a pico, and this is a nano. It actually has a name, which is an angstrom. And they usually put the So this is the picture that emerged from this whole thing. Is the nucleus is where and now the electrons, they must orbit at this distance, which is 100,000 times bigger than the size of the nucleus itself. To give you an idea, the sun is about 700,000 kilometers. The distance from the Earth to the sun is 150 million kilometers. So if you take 150 million and you divide it by 700,000, just to give you an idea to see if the picture of the solar system will fit in this model. Namely, if I put the sun instead of the nucleus, where would the Earth be? Okay, that's the question for you that I'm trying to understand. Okay, that's what I'm trying to find in here. So if you take 150 divided by 700,000, obviously the zeros cancel. And I will be left with 1,500 divided by 7, which is roughly about 200. Okay, it's about 200. Okay, 1,500, 15 divided, yeah, it's about 200 and some change. Anyway, the point being in here is that if I were to put the sun in here instead of the nucleus, and I would want to find where the Earth would be, the Earth, of course, will not be at 100,000, but rather it's barely attached to it. So in other words, if the sun represents the nucleus, the Earth would be too close compared to where the electron is from the nucleus. The electron is about 1,000 times. The electron is about 1,000 times further from the nucleus as the Earth is from the sun. That's amazing. Because if you think that there is nothing between the Earth and the sun, if you think the solar system is empty, where the sun is here and barely you're going to find dots next to it, that if you think that there is nothing between the solar system, the picture is even worse for the electron and the inside the nucleus, inside the atom. The atom is mainly empty space. Atom is mainly empty. It's actually emptier than the solar system. So the solar system presents a very, very dense structure compared to the atom is. So this is really the picture that emerged. And to help his model, basically, he when asked why wouldn't the electron fall on the nucleus, well, he says that basically, well, why wouldn't the Earth fall on the sun? So you have the sun in here, you have the Earth in here. Well, the Earth has a velocity, and that velocity will keep it from falling. So that's basically what the picture is. So his argument is that the electron has a velocity, and that velocity will keep it from falling. That does not work for the case of the atom. There is a big reason for it, okay? The Earth is neutral. The sun is neutral. And the force of attraction is due to the force of gravity. And that force of gravity is exactly what is needed to maintain the Earth in its orbit, okay? So this is basically the acceleration due to the centripetal acceleration. And this is the force of gravity, which is proportional to the mass of the Earth and the mass of the sun divided by the distance squared. So from here, you can find what velocity is needed to keep the sun from falling. I mean, if you take, for example, a string and you attach a mass to it and you swing it, the reason why the mass is not flying is because there is a tension in the string that forms. If you cut the tension, of course, it's going to fly away. And the force and the tension is exactly what is needed to maintain that mass if it's moving with a given velocity divided by r, that velocity squared. This is the centripetal acceleration that we saw when we did the circular motion. Now, the idea also is not going to work in here. Yes, you might be tempted saying that the force of attraction, which is proportional to the charge of the electron times the charge of a proton, divided by the distance squared times that constant, this is the Coulomb's law, must be equal to the mass of the electron times the velocity of the electron squared divided by the distance between the electron. So you might be tempted to solve this classically and find what the velocity is needed to keep it in orbit. But there is a problem. The problem is something known from electromagnetism. Here is what the problem is. An electron, an accelerated charge, radiate energy. Period. This is how antennas work, by the way. In an antenna, you have a charge that is going up and down in the antenna, and it's going up and down. In doing so, it's emitting electromagnetic radiation. Well, if you don't supply energy to it, it's going to slow down until it stops. But what the antenna does, it supplies the energy enough for the electron to move up and down in the antenna, radiating electromagnetic radiation energy. So what's going on in this case is, if this picture is to hold, then you have a charge. In this case, the electron is going around and it's accelerated with this very same acceleration. So if you have a velocity and it's accelerated with this velocity, with this acceleration, therefore it's a charge that is accelerated, which means that it's going to radiate energy, which means it's going to lose energy. Therefore, the nucleus sitting in here and the electron cannot stay in orbit. It's going to spiral and fall onto the positive charge. It's going to lose energy. And after it loses all of its energy, the one that has to do with the motion, mv squared over 2, that's the kinetic energy it has, and the potential energy. So it's going to convert that and until it's going to fall into its orbit. So the Thomson, or at least the Rutherford model, does not yield a stable atom. So atoms cannot exist, actually. They will all cancel each other immediately after they form. Actually, calculate the time it takes for this one, and it's a fraction of a fraction of a fraction of a second. So it's going to immediately collapse on itself if you really follow this reasoning. So the picture that is, it's similar to the like a planetary system of some sort, like the Earth-Sun system. This is not correct. So this model is not correct, and it's due to electromagnetism, where charged particles radiate energy. Therefore, this model is not going to work. But it really explains some of these experiments, like this experiment of Rutherford. That's the only way to explain it, is through a system like this one in here, where everything fits in place. And it explains a lot of other things too, including the electron, including a lot of other things, including Millikan's experiment. Everything is up to this point is good. But that's the whole idea with models. Basically, come up with something which you think is a very solid explanation, and then you have to go beyond it. And that's really the conclusion of this model, which means that this picture is not correct. So we went through several pictures at this point for the atom. We went from the ancient pictures to the modern view, to where we basically built at the end Thomson's model, which later on was basically blown away basically by his student Rutherford in his experiment. New Zealand, that's where he is from. Sometimes it's really a word, so he's from New Zealand. Okay. So, but he was actually in England at that time working with the J.J. Thomson. But the point being in here is that his picture immediately, initially confirmed the work of Thomson, then later on basically came up with a different picture. This is the model that came up with. Now, in parallel with this, there was another, and the work involved the so-called black body radiation. So what is the black body radiation? If you take a material and heat it up, it's going to, actually every material emits radiation. That's true no matter what. But if you take a material and you put it on the, give it energy, it's going to radiate depending on how much energy it's going to have. So depending on its temperature, it's going to have a pattern that looks like this. This is experimentally the observation. So if I take in here the wavelength, and if I take here the intensity of the radiation, intensity, this is how it looks like. For a short wavelength, there is little, and then it peaks around a certain value, and then it drops for long wavelengths. So that is basically how the pattern looks for a given temperature, for a given T. Now, if you increase the temperature, the pattern looks a little bit differently. First of all, it peaks in here around this value. For a higher temperature, it peaks toward wavelengths that are shorter. So a lambda max in here is different than this lambda max. So this is where the radiation peaks that is emitted for a higher T, higher temperature. This was a known experiment for the so-called black body radiation. You take a spoon, for example, or any metal, and you put it under a lot of heat, and that's what's going to happen. It's going to change color depending on how much temperature you have. That's basically how you're going to have, and this is the pattern that you have in here. So there is actually a law that connects the peak frequency, the peak wavelength. This is the peak wavelength to the temperature. As the temperature gets higher, the wavelength shifts towards smaller values and vice versa. And the constant in here was a well-known constant, 10 to the negative 9 times, 2.9 times 10 to the positive 6, actually, where this one is measured in nanometers. Remember, the nanometer is 10 to the negative 9 meters, and this temperature is measured in Kelvin. So that is basically what is known as Wien's displacement law. So this is a fact. There was another law also that emerged from this whole pattern, and the law has to do with how much energy is being basically produced. If I take this lower temperature, this area, how much energy total produced, all wavelengths considered, not just where the peak is, not for the long wavelength, which is where the red is and longer, or where the violet is and shorter. We're talking about all the entire picture. And if I take a different temperature, for example, the higher temperature is going to be this entire area. So it's actually a method that is easy to do. All you have to do is measure the area. So divide the entire graphing picture into the graph paper, and then count the squares, and that's how you find the areas. And the law tells you that the amount of energy emitted in this case is proportional, which is number 5.67 times 10 to the negative 8, times the temperature to the power 4. That's basically another law. This is actually Stefan Boltzmann law. Anyway, this observation were well known, okay? Anyway, this were well known. Here is the problem. We wanted to understand what this thing was. So Mr. Rayleigh put a model, and in his model, basically, he thought that all of this light that is coming out in here, it's excited from the different materials that make up that body. And if everyone has a similar contribution, this is the picture that emerged from his model. And it's actually not a good picture at all. So this is what has emerged. So the theoretical model matches the low frequencies, namely the long wavelengths, but then it starts to diverge for the shorter wavelengths. This goes to infinity as wavelengths become smaller and smaller. It doesn't peak at all. It continues to grow indefinitely. So this is what Rayleigh's explanation was. And this was known as, because this is, remember, the violet is somewhere in here. And the red is somewhere in here. Okay. This was known because now we're talking about the ultraviolet UV radiation. This was known as the ultraviolet catastrophe. Catastrophe. What that means is the following, that for short wavelengths, the theory doesn't work. The model that Mr. Rayleigh has proposed doesn't work. So Mr. Planck, in attempt to trying to come up with a better explanation, he came up with another model. He suggested that the energy of every single light is proportional to the frequency of that light. So this is Planck's model. In doing so, if he tuned this constant H correctly, so this is the energy, and this is the frequency. Remember, the frequency and the wavelength are related to one another through this relationship. The speed of light divided by just the wavelength gives you the frequency, okay? And this is a constant. Later on, people called it after him, and they called it Planck's constant. So at this point, he just called it a constant. It was later when it was named as constant. If you do that, and you choose the value of H correctly, so the value of H has to be tuned. And the H, of course, has the units of energy, which is joule, divided by units of frequency. And the unit of frequency is the inverse of time. So the units of H must be that of energy divided by the units of frequency, which is just 1/1/second, which is just second. So the number for it is that he has to do is 6.626 times 10 to the negative 34, and that is in joules second, which is the same thing as an action, by the way. Has the same units as an action, okay? If you do that, and you plug in the value of T correctly, the curve matches immaculately. It's amazing how much it corresponds. So the work of, it will reproduce for this T, for low T, for example, this curve exactly matches with it, even for lower frequencies. I mean, for higher frequencies and for lower frequencies too. And it's going to match also for all frequencies. So Planck's theory works beautifully. He did not understand why the energy seems to be proportional to that one. Not only that, but it's quantized also. The energy is quantized. Okay. So that is really what the whole thing is, meaning that for a given light, the energy is just an integer multiple of this number NHF, okay, for a given frequency. And this will create immediately an issue, meaning for low frequency, meaning long wavelength, remember, for low frequency, wavelength should be high or long. It's the same relationship, okay? So if you take f small, lambda will be big, okay? For the energy gap between the two is not big. So they contribute, a lot of them will contribute to the energy. Now for high frequency, meaning short wavelength, the gap, because remember, this is 1 HF, 2 HF, 3 HF. So this is 1, this is 2, this is 3. But the gap has to do with the wavelength in this case, and the wavelength is, I mean, the frequency in this case, I'm sorry, the frequency is small. But for short wavelengths, namely the UV radiation, namely this side, the F is big. So the F is big, so the gap between successive modes of excitation, if you will, for that atom will correspond to less contributions, because you have less of them between one point to the other, versus the low frequency or long wavelengths, so which will have more in this case. So in other words, yes, there is more energy for the high frequency, but there are less of them. High frequency means high energy, because E and F are more are proportional to each other. So high frequency will have theoretically more energy, but there are less of them contributing, versus low frequency, which are more of them. Yes, there is less energy per mode, but there are a lot of them. And that's what really how the curve at the end matches itself, okay? So when you increase the frequency, a lot of them, when you make the frequency as high as possible, even in X-ray or gamma rays, then in this case, the gap will be so ridiculously big so that there is only very few of them that are showing. And at the end, they don't contribute much to the pattern. So they don't, there is no such a thing of an ultraviolet catastrophe for high frequencies. Obviously, for low frequency, namely for very long wavelengths, namely for the infrared and so on and so forth on the other side of the spectrum, yes, there are a lot of them and they contribute a lot, but they have very low frequency, they have very low energy anyway. So they don't contribute much to begin with. So this is the picture that emerged from Planck's model. So the point being in here is that this model in here led Mr. Einstein actually to do something else, okay? Because there was another phenomenon at that point, and the phenomenon was the photoelectric effect. I'm going to finish today with this one, and we're going to continue the discussion later on, because we're trying to build a modern view of what the atom looked like. The photoelectric effect. Okay, I'm going to come back to the quantization, because the quantization is very critical in here. One of his biggest things that Mr. Planck contributed is this number n, that the energy is quantized. It comes in chunks, basically, of energy. And later on, we will try to understand this picture using the quantization. That really the whole point of this whole discussion is, because one of the things that we discussed is that the early experiments that were way before all of this showed that each element has its own unique spectrum, the spectral lines, and they don't change. So it seems like each one of them corresponds to a certain frequency, and that frequency is unique per element. So in order, Mr. Thomson's model would not explain that. Mr. Rutherford's model would not explain that. So at this point, we were left with a picture that is going to emerge, and the picture that is going to emerge is due to Mr. Bohr. And Mr. Bohr actually took the ideas that Mr. Planck has used in here and actually reinforced by Mr. Einstein's work. And Mr. Bohr explains, at least for the hydrogen atom, explains this spectrum. Obviously, it fails for the rest of the elements in the periodic table, but works with this element in the periodic table, but not the rest. And there are a lot of elements in the periodic table. So we're going to see on Wednesday, basically, how the whole picture fits so that we have everything together for the atom. So for right now, I'm going to finish, like I said, a discussion today with the photoelectric effect. When we come back next time, we're going to build it on the Bohr's model. We're going to understand the spectral lines, and we're going to have an emerging picture of what the atom looked like according to modern theory. Okay. So again, the photoelectric effect was a known effect at that time, and people didn't understand it. So if you have a mirror in here, and you shine light to it, and if the frequency of the light exceeds a certain threshold, so frequency has to be high enough. High enough. Excuse me 1 second, okay? Let me pause this thing in here quickly because I have somebody talking behind me. Sorry about that. Let me finish this discussion and then we will end it, at least for today. Anyway, so the picture that emerged at that time basically is that we have a light that has to have a high enough frequency. So it has to exceed the certain threshold. And that threshold now will see immediately an electron emitted. This is actually the idea behind the solar panels that you see above some homes, okay? Solar panels. So you have charges that are created. Of course, you can capture them and produce a battery if you like, or current, or whatever you want to. But the idea in here is that the frequency has to exceed a certain threshold. So if the frequency is below threshold, no matter how much light you're going to produce, even if you flood this thing in here with light. So if you have a very powerful source, it doesn't matter, okay? As long as the frequency is below that threshold, nothing is going to happen. That frequency depends on the material, by the way. The threshold depends on the material, of course. So obviously, if you exceed the threshold in frequency in here, if you put more light, if you put a flood of light, you're going to just increase the rate at which electrons are produced, that's all. But not any more electrons than this frequency in here, the frequency in here. So if you increase the frequency, obviously the number of electrons will also increase in this piece in here. No, I'm sorry. It's going to have, yeah, it's going to increase also. So here is what because again, Mr. Planck, when he suggested this idea, it explained the black body radiation, and it eliminates this ultraviolet catastrophe from being seen. But the problem with it is that he himself convinced with this quantization thing. There is no rationale for it. And furthermore, his expression was kind of lonely in there. And at that time, that constant, nobody understood where it came from. And it was a mystery, actually. Yes, it works to explain this experiment, but that's all it does. So Mr. Einstein took it a step further, and he suggested the following, that this light in here is actually, any light is made up of particles. He called them photons. That's the first time the word photon was basically made up. Mainly the particle of light. That's what photons stand for. They are particles. So when you see ON, that means it's a particle, but photo in this case is light. So photons of light. Just like electrons, particles of electricity. So that's basically what the word came up from. So now, the photons that Mr. Einstein has suggested have energy that is basically, the photons is also HF, exactly how depending on their frequency, that's their energy. Furthermore, they have actually momentum, okay? And that momentum is what causes the particles to collide with the electrons that are inside the atoms in here, and these atoms are going to be moved. So if you don't have enough momentum, If you don't have enough energy, you're not going to create that model. Okay. So these are particles, they don't have mass, so they are massless at rest. But they have energy plus momentum. Now we're dealing with a collision of two particles, namely a photon plus electron. Okay, this is the picture that emerged, therefore, that we have all of these things. Now, this model of, there was other experiments actually that were conducted at that time by, among others, were Mr. Compton in St. Louis. Was he in St. Louis? I think Washington University. And so the picture that is basically coming out now, even with this scattering that involves high energy photons, basically X-rays and gamma rays and so on and so forth, that involves other electrons inside and even some other basically anchored inside the atom. So all of this suggests that actually that light is indeed a particle, as opposed to Young experiments, for example, for the interference patterns. Those suggest that light is actually a wave. So there is a duality in here that starts to emerge, that light behaves as waves when it comes, for example, to the Young experiment, to the double slit experiment, to everyday experience. But when it comes to, for example, photoelectric effect or the scattering, light is actually a particle. Now we take this idea and we flip it on its head and think of the electrons as waves rather than particles too. So if light can do the same, can do basically particle wave in the same time, why wouldn't the electrons do the same thing? Actually, this idea was due to Mr. Louis de Broglie, who basically suggested it when he was doing his thesis. But before that, Mr. Bohr took that idea and worked with it, and he came up with an explanation for the visible spectrum of hydrogen. And this discussion, we're going to build on it next time for Wednesday session. Please watch this recording. I know I started a little bit earlier, I think around 9:45. Please, 8:45, I should say. Please watch this, all of the recordings for today, and also there will be a recording for this Wednesday. There will be no live session on Wednesday, so it's going to be pre-recorded. So if you have any questions, please let me know. Again, we have a session today and the lab session that is going to be dedicated to 4 chapters, all of them dealing with the problems related to the exam 3, namely chapter dealing with electricity, namely electrostatics, Coulomb's law, basically, the chapter dealing with the currents, namely Ohm's law, mainly, and then the chapter dealing with electromagnetism, magnetism and magnetic properties of materials, and also Ampere's law and Faraday's law and all of these things that have to do with that component. And finally, discussion of problems that have to do mainly the expression that we saw today, namely Planck's law, which gives you the energy in terms of a frequency, with that constant h being the common factor. And I posted the problems that we're going to have in discussion on in this week's session. And I'm going to try to bring with me a printout of those ones, but if you can bring them, please bring them with you so that we can have a discussion today. Thank you, guys. Any questions? TJ?
See you in lab today.
Okay, see you. Thank you.